Here we will see data management pattern in microservice architecture. Different microservice data management patterns are database per service pattern, shared database pattern, saga pattern, CQRS pattern, event sourcing pattern, API composition pattern, domain event pattern, and database sharding pattern. First, database per service pattern, which is recommended for microservice architecture. This design pattern dictates that each microservice owns and encapsulates its own private data source, which cannot be directly accessed by any other microservice, which enforce loose coupling, clear domain boundaries, and true service independence. For example, when service A gives payment request to service B, service A waits for the response to perform appropriate actions, which is based on the result from B. Here we need to handle the situation and inform service A about the result when service B is back online. Benefits of these systems are, it includes autonomy, independence, and scalability, which simplifies the database schema and make it more aligned with the microservice specific requirements. Then shared database pattern. Here multiple independent microservices read from and write to the exact same physical database instance. Even though database per service pattern is standard for microservice, a shared database is often utilized during legacy monolithic migrations or when strict ACID transactional integrity across domains is non-negotiable. It can introduce tight coupling between services, potentially leading to conflict and scalability challenges. For example, an example could be a temporary state while migrating monolithic to microservice. Benefits of these service patterns are, it includes cost effectiveness, data consistency, simplified database maintenance, and transaction management. Then Saga pattern. The Saga pattern manages distributed transactions across multiple microservices by breaking them into a series of smaller independent steps. Here each step updates the database and emits events to trigger subsequent steps, which ensures eventual consistency and fault tolerance. For example, when the order server receives the request for new order, it has to check with the payment service and inventory service. If we deduct the payment and inventory and fulfill the order, and if there is no inventory available, then we can't roll back it. It is difficult if multiple databases are involved. Benefits of these patterns are, it includes improved reliability, fault isolation, and scalability. Additionally, it enables long-running transactions without blocking other services. Then CQRS pattern, command query responsibility segregation. It separates read and write operations into distinct paths. By using separate models for reading and writing data, CQRS optimizes performance, scalability, and flexibility. Benefits of these patterns are, it includes improved performance, scalability, and flexibility in handling complex queries and write-heavy workloads. Additionally, it facilitates independent scaling of read and write operations. Then event sourcing pattern. Event sourcing captures all changes to the application state as a sequence of immutable events. This provides a complete audit trail of changes and enables scalability and flexibility in handling data. Benefits of these patterns are, it includes improved traceability, auditability, and resilience. Additionally, it facilitates temporal queries, which allows the application to reconstruct past states easily. Then API composition pattern. The API composition pattern aggregates data from multiple microservices into a single API endpoint, which simplifies client interactions and reduces network overhead. Benefits of this system include improved performance, reduced network latency, and simplified client-side logic. Additionally, it enables the creation of composite views which are tailored to specific client requirements. And domain event pattern. Domain event pattern represents significant state changes within a microservice. By publishing domain events, services can communicate asynchronously and maintain loose coupling, which enhance scalability and flexibility, but requires careful event design and event handling. Benefits of this systems are, it includes improved scalability, decoupling of services, and real-time responsiveness. Additionally, it facilitates event-driven architecture and enables event-driven processing. Then database sharding pattern. Database sharding horizontally partitions data across multiple database instances, which improves scalability and performance by distributing the workload. Benefits of these systems are, it includes improved scalability, performance, and fault tolerance. Additionally, it enables horizontal scaling of databases, which allows applications to handle growing data volumes and user loads effectively.